Oh, friends, hello, welcome back. So here we go. Start off last time looking at the limit definition of a derivative. So we're going to do just looking at some basic derivatives. So we're going to start to transition from this idea of limits over to derivatives. So what does that look like? Well, let's take a look at some basic functions. Let's let f of x be equal to c, and c can be any real number. Okay, so c, let's let that be any sort of a real number. What if I wanted to find the definition of that? So if I remember our formal definition of a derivative, we said that f prime of x equals the limit as delta x approaches 0 of f of delta x plus delta x, sorry about that, getting a little tongue-tied here, minus f of x, all of that would be over delta x. So if I were to plug that into any constant number, say for instance like f of x equals 3, notice there, if I were to plug this into our definition of a limit, there is nothing that we can plug x plus delta x into. So if I were to plug this in, or I'll use my definition of a derivative here, f prime of x, for any constant number, I'd get delta x as it approaches 0. I'd have f of x plus delta x minus f of x all over delta x. So if our function is just some constant number, then that's just going to be c. So c minus c, whoopsies, all over delta x ends up being 0 divided by delta x, which equals and any number that divides into 0 is going to be 0. So I'm not even going to plug it in. There's no reason to. So it doesn't matter. It turns out the derivative of any constant number, is 0. So the derivative of any constant number is always equal to 0. I want to look at one more little limit definition. Now, again, you guys don't have to do this, so please don't. But what if I give one more? Let me just say, let's let delta x equal h, because what I'm going to do, I'm going to have a lot of delta x's, and I don't feel like writing. What if I were to say, let's let f of x be some polynomial, not some polynomial, some exponential, or some x to some exponent. It doesn't really matter what. Now, n can be any exponent, doesn't matter. If I were to take the derivative of this, and I'm going to use h instead of delta x. So as h approaches 0, and I'm going to have x plus h to the n minus x to the n all over h. Now, we're going to, using our Pascal's triangle or binomial expansion theorem, and again, you guys don't really need to remember what that is. It doesn't really necessarily play a part in what we're doing. I just want you to know this isn't coming from anywhere. So we'd have some x sub n. If I were to expand this whole thing out, And then I'd have some constant value. Who knows what that constant value is? No, actually, I do. It'd be n times x to the n minus 1 times h. And if I were to just let this whole thing kind of play out a little bit here, then I'd be down to n, a whole bunch of terms in the middle. And all these terms in the middle have some h that is just like huge, huge exponents in general. N minus 1. It's just 1x right there. And then as we keep going here, this would be plus h to the n minus x to the n, all of that over h. Now, if I cross out my x to the n's, what ends up happening here, friends, is I end up with and again, I'm just doing a couple real quick proofs because I want you to know that these don't just come from nowhere. What we're going to be doing today, it all stems from somewhere. I have n times x to the n minus 1 times h. And remember, these h values now are going to be adding up. So that way, all of these terms will have some h to an exponent greater than 1. So if I take out an h from all of these, we have n x n minus 1 plus h times, so our next term over here, that would have been, oh, some value. I'm going to just call it a sub whatever. It doesn't really matter. X to the n minus 2 times h or plus, we have n times x to the n minus 2 plus h to the n minus 1. And if I plug 0 in here, notice what happens. This number right here, so this, if I plug 0 in for here, this whole thing, this whole term right here is going to be multiplied by 0. So the whole thing goes away. And I'd be left with just n to the times x to the n minus 1. Well, this is our second really big derivative we need to worry about. If I want to take the derivative of any x to an exponent, I notice what happens. That exponent goes in front of the x, and I subtract 1 from it. Well, that does a lot for us now, friends, because all of a sudden now we have some different formulas that we can use to evaluate a whole bunch of derivatives. So if I were to go through and erase all this real quick, like that, like so. And again, you don't need to remember those proofs at all. I just want you to remember that these all come from somewhere. We don't just make this stuff up. Well, now think back to when we did our derivatives yesterday with limits. We had some pretty ugly derivatives here. But the first one we dealt with was this, f of x, and you guys did a pretty darn good job dealing with this. and we had x squared, or negative x squared, sorry about that, plus 7x. And I asked you to find the derivative when x was 2. Well, what we're going to do is we're going to use this little formula that we got now. No matter what happens here, I can shorten these up by a lot. Let me show you how, and then we're going to practice it a little bit. Turns out I don't need to use any more derivative, any more limits at all. So if there's a negative here, that's really like having a -1. So using this first formula of ours, we have -1 times, now that exponent, this exponent is always going to go down in front of the variable. So the exponent is going to go down in front, so times 2. And my new exponent, once I drop it down, I'm going to subtract 1 from what I had before. So 2 minus 1 is 1. Plus, there is no exponent, we assume it's 1. So plus 7 times 1 x to the, and if I take away 1 from it, it'd be 0. So the first derivative would be -1 times 2 is -2x. Add one of those. Plus 7 times 1 is 7, and x to the 0 is 1, so that goes away. Turns out that my derivative is -2x plus 7, and if you remember, we figured that out with limits last time, and it took a while. But using our power rule and our constant rule, we can figure this stuff out a lot quicker. Biggest thing, we take the exponents, and we drop it in front, and then we subtract 1 from our exponent to get our new exponent. And from there, just plug and chug. So some of you are like, Williams, why didn't you just tell us this last time? And I would have saved a whole lot of issues. Probably true. But it's good for us to understand where things come from. We need to understand the notation, why things work. And then when we use that limit definition to help us out and generate these little formulas, it makes it go a lot quicker. So that's going to be what we're going to do today. Notice these derivatives are going to go a lot quicker. I'm not going to have you evaluate a bunch of them because we don't necessarily need to do that. We just need to get practice at using derivatives or taking derivatives. So let me throw some functions out here for you. And what I want you guys to do is I want you to try and figure out what the derivative, what that expression would be to find the instantaneous rate of change. We have x cubed plus 7x squared minus x plus 5. And while I'm writing the other ones up there, I want you guys to go ahead and take a little shot at that one. All right, so we're going through here. You guys are still finishing up that other one while I go through and I write all these up here. Let's do one more just for the fun of it. All right, so by this time, hopefully you got that first one done. So before I start this, anytime I don't see a number in front, I'm going to put a 1 there. I know that this has a 1 as well. So every exponent, I'm going to move down in front of the variable. And Then after that, I'm going to come back to each exponent and I'm going to subtract 1 from all of them. So if we were to do that there, so f prime of x, I mean, just imagine how ugly some of these would be if we were doing the limits here. So the 3 goes down, and then 3 minus 1 is 2. So I have 7 times 2 goes down, 2 minus 1 is 1. 1 goes down, 1 minus 1 is 0. And now look, we also have now just our constant. The derivative of any constant is 0. So when we clean it all up, we end up with 3x squared plus 14x minus 1. All right, why don't you pause the video and see if you guys can try these next ones. Now, be careful. Some of them you're going to have to rewrite the expression before you actually do it. So go for it. All right, here we go. So f of x, and I'm going to rewrite this real quick here, 4x squared minus 5x to the first plus 8. Now, I'll be honest, I don't like having denominators, so I'm going to rewrite that as 3 times x to the negative 1. Everything becomes a power rule. So, again, every exponent goes in front. Now, I know I am, and you guys will find more about this as we go through, but I'm being very selective about what functions I'm doing. We won't be able to do every function today, so I'll be dropping all those exponents down, but we'll get a pretty good shot at it. We'll at least have the gist of how these rules apply. All right, so I got 4 times 2, x to the 1, minus 5 times 1, x to the 0. I got a constant. I like constants. So this right here, derivative of a constant is 0. Minus 3 times drop. You can drop that negative 1 down. Negative 1 minus 1 is negative 2. So I end up with 8x minus 5 plus 0 minus 3 plus 3, sorry about that, x to the negative 2. I can leave my answer like that, especially if this is a free response question of the test. However, if I wanted to, I could rewrite this. I don't have to, but if I wanted to, I could rewrite this as this. I could move that x squared down to the bottom if I really wanted to. I don't have to, but on the multiple choice portion of the test, I may have to. All right, so this one right here, can't do a straight power rule with it. Remember what I said, gotta be careful. Because I have something going on inside here, there's a g of x function there. I'm going to have to multiply this whole thing out. So before I do it, I'm going to end up getting 9x squared. So I'm multiplying it all the way out because I can't have anything inside the parentheses. I can only have just straight x's. And then from there, f prime of x. And hopefully you guys are starting to see some of the patterns here. So 9 times 2x to the 1. And don't forget that there's a 1 here with this guy. Plus 24 times 1x to the 0. And a constant. I like constants, I just drop those. So f prime of x equals 18x plus 24. Even radicals. Remember how we had to do the rationalizing on our limits? Turns out, what if I just treat it as an exponent? So instead of square root, what if I make that 1/2? So f prime of x equals, drop the exponent, and then from there, got to take that exponent, and we're going to have to subtract 1 from it. So I drop the exponent, and I subtracted 1. So 1/2 minus 1, well, that'll make that a negative 1/2. I could leave my answer like that, but if I wanted to, I could go further. I don't have to. But just to be safe, I will. The x minus 1 would go to the bottom, so it becomes a positive 1/2 exponent, which is the square root. All right, again, x plus 7, right now that's to the 1 down here, right? So how about we rewrite that then? 5 x plus 7. So now take a look at it. Just like with radicals, we don't have to rationalize. We also don't have to get common denominators anymore and go through that whole limit process. Using our exponents are huge for us. We can go through and clean this up a little bit. So f prime of x equals 5 times negative 1 x plus 7 to the negative 2. In other words, f prime of x, and again, I don't have to clean it up. I'm going to, but I don't have to. These little formulas, they're fantastic. These are called our basic derivatives. And notice, they all have to deal with the derivative of a constant number being 0. And the derivative of some power, you just drop the exponent and then subtract 1 to get your new exponent. Basic derivatives. So, throw that one back up here again so we don't lose those. But I want to show another derivative. And again, you don't need to know the proof for it, but I am going to show you the proof of one of these because I want you to make sure that you have a good understanding that these don't just come naturally from nowhere. They do come from somewhere. And friends, dag nabbit, you know how much I like doing a proof here every once in a while. What about if I were to give you something like this? Let's let y be equal to sine of x. And again, just for the fun of it, again, I'm going to let delta x be equal to 8 because I'm going to have a few different variables going on here. So what if that's what we're dealing with? Let's try to find the derivative of that. And again, I'm going to have to remember one of my trig formulas here, and that's why I wanted to do this. I don't want you guys to try to do this. Some of our trig stuff from pre-cal doesn't really come into play for calculus. So here we go. Sine of x plus h minus sine of x all over h. Well, friends, I see a sum here. And if you remember, I love my sines, right? Anytime we got a sum or difference of sine or cosine, we can use our little song of sine, cosine, cosine, sine, cosine, cosine, sine, sine. I love it, man. All right, so do my little sine, cosine, cosine, sine song, the first part of that. Here we go. Sine, cosine. You guys wouldn't ever be expected to do this on your own, guys. Don't worry about this. Plus cosine sine. Minus sine of x. And all that is over h. Well, friends, just doing a little bit about just doing some factoring and grouping of terms. I would have done this. What if I were to take everything that had a sine x and put it together, and all the things that didn't have sine x, put those together? So what if I did cosine of x, sine h, and since I have a denominator of h, I'm going to break this up a little bit. Plus, what if I had sine x? Again, this will be the only time you guys see this here because there is no problems that we're going to have in this semester where we have to deal with sum and difference formulas. I just want you to understand that these things are not coming from nowhere. They're coming from somewhere. And if I were to break them up a little bit, well, if I go one step further, so I have cosine of x sine h all over h. And notice that these both have a cosine. So I'm going to take out a negative sine x. By doing that, taking out a negative sine x, I'm going to end up with 1 minus cosine h. Some of you are going, oh, wait a minute, I see where this is going. You do? That's awesome. You don't? That's okay. All right, see if we can't try to clean this up a little bit more. Because now I can break stuff up just a tiny bit more. What if I separate all of these with a limit? So what if I said, so take the limit of this as cosine h, because with my limits, I can multiply all these out. And this would be sine h over h. So that'd be our first part. So you can kind of see it. Here's the cosine. And then I have the sine over h. And then, if I'm still going through here, I'm going to have a minus. Let's see here. I have a limit of, oh, what's that? Sine x. And I'm going to multiply that by the limit and friends, I'm hoping that you guys are seeing a couple of our corollaries of the squeeze theorem that we had. For instance, right here. For instance, right here. So if I plug my values in here now, I plug 0 in here, well, there's nothing for 0 on the first limit, so I get cosine of h. I lied, I get cosine of 1. Although it would have helped if I would have made that the right thing here. It's supposed to be x right there. Thank you. So I get cosine of x times, well, sine h over h, when it's h is 0, that would be 1, minus sine x. And then I'm going to be multiplying that by 1 minus cosine h over h when h is 0 would be 0. And friends, kind of looks like I'm left with cosine of x. So it turns out if f of x is sine x, turns out cosine is a derivative of sine. Again, you don't need to remember that proof at all, not at all. But I wanted to spend the time. I thought it was important that you guys know and realize, hey, these aren't just coming out of nowhere. They actually come from someplace. Now, you don't ever have to prove them yourselves. That's not what calculus is about. And then I'm going to go ahead and give you the cosine one as well. Cosine x, turns out that is equal to negative sine x. And we get our first of our 4 little shortcuts. So let's get rid of this. You don't need to do that again. Ooh-wee. You don't need to remember that. And what I'm going to have you guys do, you're going to be ever so kind here. Let's see here. Let's have you try one of these. Yeah. Why don't you guys go ahead and figure out what is the derivative if I tell you the function is f of x equals sine of x plus 3 plus cosine of x minus 2. Well, I erase the rest of this to see if you guys can actually figure out what would be the derivative of that function. What is f prime of x? All right. It's really as simple as what is the derivative of sine? Derivative of sine is cosine. And change sine to cosine. What is the derivative of cosine? Derivative of cosine is negative sine. Change cosine to negative sine. So f prime of x equals cosine of x plus 3 minus sine of x minus 2. And there you go. So even trig isn't bad. Even trig is not bad. Well, friends, let's go one step further, shall we? What if I tell you f of x is, let's see here, x cubed minus or plus 2x squared minus 3x minus 1. Here's what I want to know. I would like to know what f prime of 1 is. I would like to know the tangent line, the equation of the tangent line. At x equals 1. And then the last part is using that tangent line, I'd like to know the linear approximation of f of, well, let's try 1.1. So kind of like what we did yesterday with limits, but notice it's probably going to go a lot quicker now. So I'd like to know f prime of 1, the equation, that's a q right there. There you go. The equation of the tangent line at x equals 1, and then the linear approximation of f of 1.1. Go for it. All righty, here we go. So, first up, the derivative. If I know that f of x is x cubed plus 2x squared minus 3x minus 1. And don't forget, this has an exponent of 1. So we're going to have a whole bunch of power rules. So all these exponents are going to go down in front, and then I'm going to subtract 1 from them. It's going to go down. Subtract 1. Goes down, and again, I'm going to show every step on it. But you guys are probably getting to the point where you're doing this a little bit quicker. You guys are starting to probably take out a step here. So 3, then 3 minus 1 is 2. 2 goes down. 2 minus 1 is 1. 1 goes down. 1 minus 1 is 0. And then my personal favorite, the constant number. Derivative of any constant number is 0 to the hero. So that means my derivative is 3x squared plus 4x plus minus 3. So there's our first derivative. Now we can use that to figure out what f prime of 1 is by plugging 1 into this. And we'll figure out the derivative, the instantaneous rate of change when x is 1. And friends, that'll be 4. So f prime of 1 is 4. To get the equation of the tangent line now, we're going to have to go ahead and plug 1 into the original equation. So we end up with 1 cubed plus 2 times 1 squared minus 3 times 1 minus 1. So we get 1 plus 2 minus 3 minus 1, which is indeed, friends, negative 1. So the equation of the tangent line is y plus 1 equals our derivative, the slope, 4 times x minus 1. And last and certainly least there, friends, we can go ahead and find the linear approximation. So the linear approximation of 1.1 using that tangent line, that would be about 4 times 1.1 minus 1 minus 1. So that'd be 4/10 minus 1, which is 6/10, a negative 6/10, or negative 3/5. And one of the big things is in AP Calculus, especially for our FRQs, we do not simplify our expression. So I would actually, if this was an FRQ problem, I would actually left my answer like that. I wouldn't have simplified it at all. All right, one final thing. One final thing, friends, and then we're going to call it a day. How does this relate to maybe something physics related? Something called particle motion. So first up, again, quick review. Average rate of change. Well, that's slope. And for our case, in particle motion, we're dealing with position and velocity and acceleration. So we'd say then the rate of change for a particle motion would be velocity. So average rate of change is slope, therefore average velocity is slope. Likewise, instantaneous rate of change is a derivative therefore instantaneous velocity is a derivative. So we have this idea that we can apply to particle motion. I know the position of a function. I can use that to help me determine its velocity. If it's average velocity, then I'm really looking at the slope between two values. If it's instantaneous velocity, then I'm looking for the derivative at a point. Well, let me give you the equation of a function, and we'll put in a little bit of context. So say I'm dealing with an equation like this. S of t, that's a cursive S, by the way, equals negative 16t squared plus 64. And what's going to happen here for this? What we got going on here with this equation is this is the equation of a falling object falling from 64 feet, where t represents time, and S of t represents feet. So 3 quick questions we're going to be dealing with, and we'll call it a day. How long until the object hits the ground? What is the average velocity of the object as it falls? What is the instantaneous velocity? Instantaneous velocity. When it hits the ground. All right, so let's see if we can do this real quick. When it hits the ground, the height of any object when it hits the ground, so let's think here. I got some object starting at 64 feet. So this is our, we'll let this be our position. And we're going to let this be time. Somehow this object is going to be falling. It's a quadratic, it's falling. But when it hits the ground, the height is 0. So I'm going to plug 0 in here. So 16t squared equals 64. T squared equals 4. Not to be confused with T Swift. It just came out with a new album. Actually, I kind of liked it. And then we take the square root. We find out that t, the time is plus or minus 2. Now, friends, I don't know about you, but I'm not dealing with negative time, so we're just going to deal with the positive time. So it's going to take 2 seconds for the object to hit the ground. Okay, so that was part A. Part B, what's the average velocity? So that's our slope. So first of all, when we drop it, S of 0, that is 64. When we let it go, it's at 64 feet. It hits the ground at 2 feet, all right, 2 seconds. So average velocity is slope. So 64 minus 0 all over 0 minus 2. So that'd be negative, or 64 over negative 2. And this would be negative 32. Now, it's okay for our velocity to be negative value. That just means that it's going backwards or going back to the beginning. By the way, 64 and 0, that is some measure in feet. This down here is some measure in seconds. So for velocity, we got to make sure that we give it a unit of measure. That would be feet per second. Velocity is always going to be measured in some position divided by some time. Some length divided by some time. Okay. All right, last part. Our instantaneous velocity. Well, we know it hits the ground at 2 seconds. So I'm going to evaluate the derivative for this when it's 2 seconds. Think about it for a second. Do you think that instantaneous velocity is going to be more or less than the average velocity? It's going to be more, I guess I should say, is it going to have a larger negative number or a smaller negative number? Okay, so when I find velocity is going to be equal to the derivative of position. So we end up with -16. And don't forget, take that exponent, drop it down, subtract 1 from it. -16 times 2, t, 2 minus 1 is 1. And then everybody's personal favorite, you know it's my personal favorite derivative, at least for now. The derivative of 64, any constant number, it would be 0. So that means my velocity, or my first derivative of position, would be -32t. So if I want to find that instantaneous rate of change when it hits the ground, plug 2 in there. Average velocity, average rate of change is slope. Instantaneous velocity, instantaneous rate of change is a derivative. It's -64 feet per second. All righty, friends. Did a great job sticking with today. So now you get a chance tomorrow morning to practice this a little bit and see how you do with it. Okay? All right. Have a great night.